Alright, so in this particular video, I will show you how to find the angular momentum of a particle or point mass moving in a two-dimensional plane. So here on the screen, we have a y x plane. So nothing funky, nothing tricky. So just a two-dimensional plane. All right, so here's an example. Here you can see on the diagram, you have a mass or a particle of 100 grams is moving up in the y direction with a velocity of 4 meters per second. And then the coordinate here is given as 2 in the y direction and then 3 in the x direction. All right, so all we have to do is really just find perpendicular stuff. So to find the angular momentum, you can apply this particular function, L is equal to CR perpendicular to P, where P stands for linear momentum. And the coefficient for C in these particular problem is going to be a 1 because a point mass has a coefficient of 1. So why I write it out for you, you can just ignore it moving forward for these types of particle problem. Okay. All right, so we can go ahead and expand P into M and V. The function for linear momentum is just mass times velocity, what you see in that second line there. And then from there, I can go ahead and ignore C, because again, C is just a 1. So I can go ahead and leave that out of the next line there. And then I pull mass out, because mass is just a scalar quantity, or aka in this case, it is just a multiplier of this particular cross product R and V. All right, so the first thing you want to do is trace out your r vector. So in this diagram, from the origin up to the mass, there's that blue vector r there. And then that coordinate system is going to be 3i plus 2j. 3 for the x coordinate, and then 2 is for the y coordinate. So it follows the x and y coordinate system. Okay, it's just written a little different because it's an ijk notation. All right, from there, we can break up R into Rx, which you see is the component that I just gave up on the screen. Once again, there is Rx. And then we can break R up into Ry as well. But keep in mind that when you do angular momentum, you need stuff that are perpendicular to each other. So in this case, we need R and V that are perpendicular to each other. So as you can see in the diagram, Rx is perpendicular to the velocity vector, which is in the y direction. So I'm going to go ahead and clean this up a little bit. Why you can find the component for Ry, you don't really need to, because Ry parallels the velocity vector in this problem, and we don't need that. We need Rx. So Rx and V in this case is really Vy, and those two pieces of information are perpendicular to each other. And then from there, we can just do a little plug and chug. Okay, so you notice there the velocity vector is just written as 3j. From here, we can just go ahead and expand this into Rx, and then that's V and Vy. Just keep in mind, again, it's perpendicular. And then we can just plug in the mass value. The mass value in this particular problem is given as 100 grams. I went ahead and convert that to kilograms for you, which is 0.1 kilogram. Rx in this particular diagram is 3 meters. So if you look horizontally, the position there or coordinate there for the x direction is 3, and that's where the 3 comes from. In this case, Vy is really your velocity vector, because the velocity vector is straight up. It's not tilted or anything like that. So the value for meters per second is plugged in there. And then calculator work time will give you an answer of 1.2 kilogram times meter square over a second. So that's your outcome. All right, so to do this slightly a little more complicated or formally using math, using cross products. So here is the typical format. Again, the C is left out in this particular function because it is just a 1. So I carry down mass R, and you're going to take R cross V. And then the 0.1 in the front of the matrix here just represents the mass value. I left the units out because just to save some space. Okay, so the 0.1 represents your mass in kilograms. And here's the general format. And then so Rx, Ry, Rz, Vx, Vy, Vz. And then these numbers, they come from the R vector itself. In this case, 3 is I, which goes there. And then this is a positive 2j, so the coefficient of 2 goes there. And you notice here it is a two-dimensional plane. There is no k value, so k is just 0. And likewise with the velocity vector. The velocity vector here is just straight up the page. It is not tilted left or right. And again, there's no k value here, so the velocity vector can just be written as 3j meters per second. So there's no I value here. So for Vx, we just put a 0. Vy, we put we put a 4. And then for k, we put a 0 because it's not tilted. Okay. Other than that, we just do the cross product. So I carry the 0.1 down in the front of all the work there. And where my cursor is circling, that is the general function to take the cross product in this particular instant. Okay, so in case you don't have cross product, watch. So first, to find the vector I, we cross out I, and we just concern ourselves with j and k. So to find I, we take j cross k, and what's left over there is in this line there. That's just to help you visualize where things come from. And then the next thing we do is we find the j vector. But to find j, you mentally or visually block out j, and you would take I cross k. So that left over there is carried down there, and then and so on and so on. Okay, so if you're listening to find k, you would just mentally visualize crossing out k, and then you would just keep I and j. So Rx, Ry, Vx, Vy is right there. And I didn't do that step for you because it's kind of the same process. All right, other than that, all these numbers here, they come from this particular section, 320040. So again, I'll guide you through the first box here. To find I, we mentally erase I. So all we have to do is keep J and K. So the value 2, 0, 4, 0 comes from that chart. And that's your I vector. And then you can do the same process for this section here and then this section here. So if you need to, pause the video and kind of know where all the numbers come from. Other than that, let's do the cross product. Okay, so again, I carry the mass down. In this case, we would just cross multiply everything in each of these section, and then subtract or take the difference in each of these segments. All right, so if you plug in all the values correctly, ry in this case, again, ry up here in the chart is a 2, and then VZ is just a 0. VZ is right there. That's just a 0. So it'd be 2 times 0 minus RZ. If you go up to the chart, RZ is right there. If you go to the right of that, that's just 0. And then we multiply the VY, but VY is in the middle here. And if you trace it across to this information, and that is a 4. So just make sure you do the same process for the rest of my work that's shown here. But again, hopefully you're paying attention to what cancels out. So you notice here in the first segment, you have 2 times 0, which is 0, minus 0 times 4, which is 0. So that's kind of redundant. And then in the middle segment here, you have 3 times 0 minus 0 times 0. That's also redundant. So I'm going to go ahead and cross that out. And then last but not least, this 2 times 0 for the k vector is going to cancel out because 2 times 0 is just 0. So really, we're just left with 3 times 4. Okay. So all this works is just show you how to do cross product if you're asked to do so for like a free response question or your college professor asks you to do so. All right. Other than that, we just carry it down as 0.1 times 12. And in this case, in k hat, and the unit for angular momentum is kilogram meters squared per second. But we don't really need to concern ourselves with the direction because the question originally in the statement asked for just the magnitude. So really your answer would just be 1.2 with the proper units there. Okay, you don't need the k hat and stuff like that. All right, I hope that helps. Let's move on to another example. Okay. All right, so in this particular one, it's a little different where you have now V is given as a slanted diagonal in the fourth quadrant. So that's going to have components. So again, here we have a 200 kilogram mass, and it just asks us to find the magnitude of the angular momentum. So we would start with the same format. First, I highly recommend that you just draw out your R vector. And your R vector in this case is that blue diagonal is 1 to the right and then 2 up. Okay, so let's go ahead and give the precision vector information here. So R in this case would just be I. It's just I because the position here is just a 1 plus 2j. Again, the 2 comes from the y-axis there, and the unit is in meters. So I went ahead and break it up again into Rx and Ry. It's important because you want to focus on just perpendicular stuff. So here we have Rx, which is pointing right, Ry, which is pointing up, and the resultant vector, which is this position vector here relative to the origin. But you notice here V is in the fourth quadrant, so it's going to also have components. So the component for V is going to be to the right and down. Okay. So here we have the angle here is 45, and so Vx would just be V cosine of 45. But from a unit circle, cosine of 45 is just radical 2 over 2. So that's where all this information comes from. Again, you can do the same for Vy. Vy would just be V, the vector itself, times sine of 45. So sine of 45 is just radical 2 over 2. And I put the negative sign there because it is directed downward. But you won't need it in the next step because we're just going to see how things rotate and add or subtract whether it rotates with or against. Okay. So I went ahead and kind of carry the stuff down here for you. I carry Rx and Vy down because those two are perpendicular. And then we would just attack each one. So if you can visualize the pivot, the origin is there in the diagram. So that's where the tip of the blue, the starting point of the blue arrow is. So that's your origin. So I visualize the green arrow as a force. And if you were to pull that blue arrow down this way, it would cause the system to rotate clockwise. So this is important. You have to identify what the direction in which it rotates. Otherwise, you add or subtract incorrectly. Okay. So I would just start with L equals MRV. In this case, I'll use RXVY because those two are perpendicular to each other. And from the diagram, we have all the information. M is just 0.2 kilogram. Rx in the diagram is just a 1. And then Vy, while it is negative up here, I just put a positive quantity, just a magnitude, because I know which way it's going to rotate. And it's going to cause this particular system to rotate clockwise. So I just need the magnitude here. Okay, so if you do calculator work, you'll get the magnitude of 0.424 with the proper unit for angular momentum there. But you're not done yet. So the next thing I pull to the right side of the screen is Ry. But if I use Ry, then I'll need Vx. And so I'm going to pull Vx there because those two do form a perpendicular uh, product, excuse me. And then you got to visualize the pivot at the very end where my cursor is kind of circling here, because that's quote unquote where the origin is. So if this is your arm and you're pulling this arm to the right, it will cause the blue arrow to rotate also clockwise. So in this case, you have clockwise and clockwise. Okay, so do the same process for this one, except the only difference is instead of Rx and Vy, we use Ry and Vx. So Ry is 2 from the diagram, and then Vx is the same as Vy because the angle for this one is 45 degrees. So I just carry everything down there for you, and calculator work will give you a product of 0.848. However, both of these diagram will cause the system to rotate clockwise. So we would simply add up the two magnitude. So the two magnitudes in this case would be 0.424, 0.84, both are clockwise, and therefore we would just sum it up. So the magnitude of the angular momentum for this one would simply be 1.272 with the little rounding difference. Okay. All right. However, to do this particular problem using cross product, which I don't really recommend, but this is formal using math. So there's your R vector. We can write our R vector as I plus 2j again. And then we can do the same with the velocity vector. The velocity vector is just 3 cosine 45. And then in this case, Vy is a negative value. So I put a negative sign there. That'd be 3 sine of 45 for you. Okay. But then substituting in cosine of 45 and sine of 45 from your unit circle, cosine of 45 is just radical 2 over 2. Likewise with sine of 45. And then the negative sign, because Vy is directed down, because this velocity vector has a horizontal component in the positive direction and a vertical component pointing down. So simplifying stuff, 3 radical 2 over 2 would just be 2.12, and then the I is there. And likewise with the j component, which is also the same magnitude because all these values are the same. So all we have to do now is set up our matrix again for the cross product. Mass is 0.2 from the statement there. Again, that is in units of kilograms already. And you would just set this up, Rx, Ry, Rz, Vx, Vy, Vz. And the numbers, again, from here comes from the R vector. The R vector here, this is 1i, this is a 2j, and there's no k because there's no third dimensions here. So it'd be 1, 2, 0. And then for the velocity vector, we can pull the information out here. It'd be 2.12 in the I direction. That's 2.12. And then for the j, it'd be negative 2.12. And that's where the negative value comes from. It's important that you pay attention to where you need to include the negative sign in this method. Okay. And then k is just 0. So we can just expand this, bust out the formula for cross product, which is where I'm circling again. Pay attention to that negative sign and that plus sign. Know what goes first. In this case, it has to be minus and then plus there. And then fill in the chart to the right of that. So I'll do the first one just to show you again in case you didn't pay attention to the last example. So to find I, we mentally cross I out. And to find I, we take a J cross K. So we would just keep RY, RZ, VY, VZ. And that's what that box is. And that's going to carry it down to here. And then likewise with the next segment, so to find the J vector, we would not need the information there. We would just take I cross K. So I cross K leaves us with that, and that's where this box is going to come in. And all the values to the right side of the equal sign, where my cursor is now up, is from this particular chart. So for example, RY in this case, okay, RY is right there. That's in the middle. That's a 2, and that's where that 2 comes from. And then RZ, RZ is right here, and RZ is this value in the K direction. That's a 0. And then VY is in this chart. It lies in the middle in this segment here, which is negative 2.12. So I just carry that down. And then VZ, which is right here to the right of this, it would just be 0. So you can fill the rest of this out again at your own leisure if you want to pause the video and make sure things are in the right spot. And then from there, we just cross multiply and take the difference. So for example, it'll be 2 times 0, and then it'll be 0 times negative 2.12, which I have on the screen here for you. Okay, so make sure all the values are in. I put everything in here for you. So it'd be 2 times 0, 0 times negative, and then in the next one it'd be 1 times 0 because you're crossing. 1 times 0, which is right there. It'll be 0 times 2.12, which is right here. And then this would be 1 times negative 2.12. So there's my 1, there's my negative 2.12, there's my negative because we're taking the difference, and then there'll be 2 times 2.12. In parentheses, I have 2 times 2.12. And then we again recognize that we're multiplying by 0 in the first segment here. That's going to be useless. And then in the second segment, I have a 0 there. I have a 0 there. So we're multiplying both those terms by 0. So that's again, it's useless. So we just cancel it out. So if you do careful calculator work, this whole entire third segment should leave you with negative 6.36. Okay. Other than that, we take that value and we times it by the mass which is given, which is 0.2, and we will get the same response of 1.272. Again, it asks for magnitude, so in this last line here, I left out the k hat for the direction because it didn't ask for the direction. All right. Other than that, I hope you can see how to attack these types of problem using cross product, or you can just think of how things rotate in the plane. Okay. All right. Good luck. Stay nerdy and don't be whack.